In unit number 3, we will introduce you to neural networks that have been very popular and very useful in solving very realistic problems in practice, from human level or superhuman level game playing to self-driving vehicles. Neural networks are really composed of very simple units that are akin to linear classification or regression methods, and you will see operationally how they build from that understanding. We will introduce you to several different kinds of neural networks, from simple feed-forward neural networks, think of visual processing in your neural system, to recurrent neural networks that can model sequences and map sequences to class labels and even to other sequences, say in machine translation. So the project in this unit is image classification that builds on a very specific architecture designed for processing images. It's called convolutional neural network, and you will see what advantages that architecture has over very simple feed-forward architectures.
Welcome back. Today we're going to be talking about feed-forward neural networks, and these lectures are going to be in 2 parts: understanding them as models and then learning them from data. So we will start with a motivation in relation to the type of models we've already seen, nonlinear predictors. Then we'll talk about feed-forward neural networks, what they are and what they can capture. In particular, we'll talk about the power of hidden layers. This is the first part. And in the second part, we'll talk about how to use simple stochastic gradient descent algorithms as a successful way of actually learning these complicated models from data. So let's start with the motivation. Here we have a model that we've already seen, a simple linear classifier taking as input an expanded feature representation from an input vector x, associated parameters theta, passed through a sine function, and getting the classification decision. Now let's write this model slightly differently so we start understanding these as neural networks a little bit. So I'm going to introduce here a node for each of the input vector coordinates. So first one stores the value of x1, second one stores the value of x2, and all the way to xd. So each of these nodes holds the value of the coordinate of the input vector. Now, once this whole x vector is presented to this nonlinear model, x is mapped initially to a feature representation, phi of x, which I will also denote in terms of nodes here. So there will be potentially a lot more nodes. And the first node here is the first coordinate of this feature representation, second coordinate of this feature representation, all the way to, say, capital D coordinate of the feature representation. This could be, for example, the polynomial expansion as we've been talking about. Once we have this feature representation, then we take a linear combination of these coordinate values to produce the classification decision. So I'm going to introduce a node here for this final operation that takes the sine function of a weighted combination of these features, and we have weights that are now theta 1, theta 2, all the way to theta d. There are as many coordinates of theta as there are coordinates in the expanded feature representation. Now, one particular aspect of this way of solving a nonlinear classification problem is that how input x is mapped to a longer feature representation, phi of x, that mapping is fixed. It's not tailored to the task that we are trying to solve. So this is the particular difference between a nonlinear method like a kernel method and a neural network. Neural network tries to optimize the feature representation for the task that you're trying to solve. So in some sense, in terms of deep neural networks, we are talking about representation learning, learning to represent the examples in a way that is actually helpful for the eventual classification task. You can appreciate that this task is actually quite a bit harder than the task that we've presented here. The reason is that in order to do a good classification, learn the parameters theta here for the eventual classification decision, we would need to know what that feature representation is. On the other hand, in order to understand what a good feature representation would be, we would need to know how that feature representation is exercised in the ultimate classification task. So we have a bit of a chicken and egg problem here, and we need to learn these things jointly, trying to adjust the feature representation together with how it is exercised towards classification task. So this task is quite a bit harder, and learning these complicated deep architectures will be difficult, but we will succeed in doing that even with simple stochastic gradient descent methods. Our feed-forward neural networks don't actually look very much like real neural networks in the brain. To that end, let's take a very brief look at what real neural networks look like and then abstract them away towards our artificial neural networks. Real neural networks are composed of cells called neurons. They aggregate signal through dendrites, and there are about 1,000 to 10,000 connections that are formed by other neurons to these dendrites. The signal from the connections, called synapses, propagate through the dendrites into the cell body. The potential increases in the cell body. Once it reaches a threshold, the neuron sends a spike along the axon that connects to roughly 100 other neurons. So you have these highly connected parallel signals that are propagated in a temporal fashion. Our abstraction of this network is in terms of a simple linear classifier. So real neuron is mapped to a simple linear classifier where the input nodes or input coordinates here take the role of the synapses in the dendrites. The weights or the parameters associated with these input coordinates try to mimic the strength of the connection that propagates to the cell body. And then the response of a cell is in terms of just a nonlinear transformation of the aggregate signal. And the output is simply a real number, not actually a temporal signal that's propagated through. Okay, let's look at a little bit more formally what our neurons look like. We will also call these units. So we have the input vector. Each coordinate is an input unit here. Its input node or unit here holds the coordinate value. We have an associated weight, and we will denote the weights here in terms of W's rather than the parameters in a linear classifier that were previously denoted by theta. So I have a weight here associated with each input coordinate. And then I take a weighted combination of that input signal. So I have a weighted aggregate input to this neuron. Z is just a sum over the input coordinates, d of them, xi times the corresponding weight. And then we will also add an offset parameter w naught. And that's typically not represented graphically here in terms of the unit. Once we have the aggregate input, we will pass that through some nonlinear function here, f of z, which is typically nonlinear, called an activation function, transfer function, or simply an output of this neuron. So here we have the input, and the corresponding output. And it functions very much like a simple linear classifier. All right, so let's look at what that nonlinear function can be. So a simple one is simply keeping it as a linear, so as a function of the aggregate input, the output of this neuron or unit would just be a linear. So that's one possible transfer function, and we will use this typically at the very end before measuring the loss of the predictor. Another possibility is a nonlinear one called a ReLU. It takes the aggregate input and simply squashes all the negative values. So this ReLU unit now, rectified linear unit, is simply defined as f of z is just the max of 0 or the aggregate input. So when aggregate input is positive, it simply passes it through. When it's negative, it squashes it down to 0. The last type of unit that we will consider mimics the sign function that we've used for a linear classifier, but now makes that sign calculation in a soft way. So if I have here -1 and 1, then the output looks like this, and this is simply the hyperbolic tangent unit. All right, so it has around 0 when the aggregate input is close to 0. You have this linear region, and then it plateaus out towards 1 or -1, whether you're going in a positive or negative direction. And this smooth version of the sign function is helpful since we have to propagate the training signal through the network in order to adjust all the parameters in the model. Later on, we will also abstract these away a little bit more. We can think of them as little boxes that take as input the coordinate values of the input vector and calculate some output. And that calculation is mediated by parameters w. So we will try to connect these boxes, whatever the computation is inside. It is parameterized by w, and that computation is affected by w. So we can learn the parameters of the w such that this unit, in the context of the whole network, will then function appropriately. And we will get back to that learning problem in a little bit. So we will connect these abstract little neurons into highly parallel architectures. And in feed-forward neural networks, these units are arranged in layers. From the input layer, where each unit holds the input coordinate, through various hidden layer transformations until the actual output of the model. Now, in this layer-wise computation, each unit in a particular layer takes input from all the preceding layer unit, and it has its own parameters that are adjusted to facilitate the overall computation. So the parameters of that unit are different from parameters associated with another unit in the same layer. So we have the input layer here, various hidden layer units, and all the way to output layer units. We say that each layer has width, which is just the number of units in that layer, and the overall architecture has depth, which is just the number of layers of transformation until we get to the answer. So if the input example X is an image, then you can think of this deep architecture as mimicking how early visual processing operates in a human or animal brain. So the input example is a pixel image. So the input layer units store those pixels. The next layer units could be just simple edge detectors, different detector for each unit in that layer. And those edges are then combined together into parts in subsequent layer until we get to objects and finally characterizations of the scene that may be something that we are actually trying to make the architecture learn. So more broadly, these type of deep architectures, deep parallel architectures have become tremendously popular and effective across areas. They overtook computer vision in the course of a few years. Similarly, natural language processing speeds, computational biology, and so on. They've been effective in more corporate applications, self-driving vehicles, conversational agents, assistants, game playing, and so on. And there are a number of areas that are actively incorporating deep learning architectures to perform prediction and control. So then there's a question of why they have become so popular and effective. And there are really 4 reasons for that. Number 1, we now are collecting lots of data, and that enables us, in principle, to learn very complex, rich models. So we can solve more realistic tasks. Reason number 2 is that we can actually computationally handle those highly parallel architectures because we have computational units such as GPUs and tensor processing units and things of that sort that can effectively handle these layer-wise parallel computations. Reason number 3 is a little bit more subtle. It turns out that these architectures are actually easier to learn as large, rich models. About a decade or more ago, we already had these type of architectures, but they were hard to learn because as small models, they were quite rigid from an optimization standpoint. But when they become richer and flexible, even simple stochastic gradient descent algorithms are actually quite effective in learning these from data. So that is a happy coincidence that occurred. Reason number 4 is that we can easily compose these models together to perform very interesting computations. So they serve as very flexible computational Lego pieces that can be adapted overall to perform a useful role as part of a much larger, richer computational architectures. Okay, let's look at these models in a little bit more detail now, trying to understand them, how the computation is performed, and how to visualize what they can and cannot do. So here I have a simple 3-layer neural network feed-forward with input layer, 1 hidden layer, and 1 output unit. The computation in this model is carried out as follows. Each of the hidden units first aggregate a weighted combination of the input units as the aggregate input. So for example, Z1, the aggregate input to this first hidden unit, is computed as the sum over the input coordinates. In this case, there are only 2, xj times the weight from that coordinate to the first unit, and then we also add that offset parameter. Then we pass that through a nonlinearity. So f1 is computed as the nonlinear function of that aggregate input. And in this case, for example, it could be the tanh hyperbolic tangent function of the aggregated input. And similarly, for evaluating the aggregate input for the second hidden unit and the corresponding output. So once we have the hidden unit activations computed in this way, then we proceed to the final output unit, take a weighted combination of these activations, get the aggregate input to the output unit, pass it through nonlinearity, or in this case, it's a linear unit, pass that aggregate input directly as the output of the model. All right. So now we can understand these type of models in terms of boxes, how the input is first transformed into the hidden unit activation. So we have a box with parameters W that takes two inputs, X1, X2, gives two outputs, F1 and F2, and this computation here is now mediated by parameters W. And we are going to try to understand how this computation changes as a function of W. Then we have the other box here that takes in the two activations of the hidden units, F1, F2 as an input, and produces the final output. And then there is some additional parameters W that mediate that interaction or computation. And we have now composed these two boxes together to perform the final computation. All right, so what we're going to do here is trying to understand what the hidden units give us in this model, what type of power we get by initially transforming the input into the hidden unit activations before we do that final linear classification. So to that end, let's understand visually what these hidden units are actually doing. Since they are like linear classifiers, they take a linear combination of the inputs passed through that nonlinear function. We can also visualize them as if they were linear classifiers. So, for example, Z1 here is now a linear combination with that, let's say, W1 vector in a product with the X as a vector plus that offset parameter, where that vector now is simply the combination of the two weights associated with the first hidden unit. All right, so it can be characterized as a linear classifier. So when that hidden unit aggregate input is exactly 0, we get that decision boundary. It's oriented similarly to a linear classifier in terms of the parameter vector W1 here. So we can understand the first hidden unit here in terms of X1, X2 coordinates as a linear classifier, where this is now the W1 vector. Okay? And the decision boundary here corresponds to when the aggregate input to that unit is 0. So if we have a tanh activation, then we don't get just a positive negative sign on either side of this decision boundary, but we get a graded response. You can think of the function going towards -1 as we move in the negative direction from the decision boundary, and it's going towards 1 as we move in the positive direction. And the quicker it makes that transition, the larger the norm of the parameter vector W1 is. All right, so now we can do the same thing with the other hidden unit. As a result, if I draw it here, we can now understand both of these. So this would be the W1 vector, the first hidden unit, and then we would have another hidden unit here with a different parameter vector describing its behavior. So we can understand the behavior of these units, how the parameters are changed. They change visually what they look like as linear classifiers. And we can understand this feature transformation by exploring how the transformation depends on our visual writing of these hidden unit parameters. So let's take an example here. I have here negatively labeled points as red points here, and then positively labeled points as plus blue pluses here, and there's another cloud of negative points here. So clearly this problem in terms of x1, x2 coordinates is not linearly separable. Now what we're going to try to understand is if we transform this x1, x2 points into feature representation, what does it look like? Does it become linearly separable now for the final output unit in terms of the hidden unit activations? Okay, so first we will draw the hidden units here exactly as vectors as before. So here's the parameter vector corresponding to the first hidden unit pointing in this direction, the parameter vector for the second one pointing in the opposite direction. And now, based on this visual specification of the two hidden units, their associated parameters, we can now understand how this transformation is going. So let's ask what happens in the very simple case where the hidden unit nonlinearity is actually just a linear one. So there's no, they just pass on their aggregate activations through the unit. Okay, so here I have circled one point here. We can ask where is that point in terms of the F1, F2 coordinates. Once we process it through the hidden unit activations, where does it lie in the new coordinates corresponding to these hidden unit activations? So that circled point here has clearly a negative value for the first coordinate. It has a large positive value for the second coordinate. So as a result, that point would lie somewhere here. Now here's another circled point, now a positive one. It's somewhere in the middle. It's positive in terms of both F1, F2 coordinates. So it would lie somewhere here. And finally, we'll take a point here. Now it has a large positive value in terms of the F1 coordinates and a negative value in terms of F2, so it would appear somewhere here. So if we now collect these together, what we get is that we take each one of these points, we pass through the network, we look at the F1, F2 coordinates that are associated with that point and plot that in the new coordinates. So what we've mapped here is how this cloud of points using these specific hidden units is mapped into the hidden unit activations. The problem here is that it's not linearly separable, right? Even though we passed it through the network, in terms of the new coordinates, it's no easier problem to solve for the final unit. So if we add here simply retain the same specification of the hidden unit parameters, but we turn that linear activation unit now into a nonlinear activation unit, we can find the last unit easily in such a way that the problem becomes separable with respect to the hidden unit activations of the original points. This is really where the power of the hidden layer lies. It gives us a transformation of the input signal into a representation that makes the problem easier to solve. We can also look at what happens with ReLU activation units. So now the problem is slightly different. The transformation, the nonlinear transformation in terms of the F1, F2, the hidden unit activation coordinates, looks different. The points are mapped now differently. As a result, if you see that both of these units have have the positively labeled point in the positive side of the decision boundaries, whereas the negatively labeled points now fall for one or the other in the negative region, and as a result they will be squashed down to zero either here or in this direction. Now, this is not actually, even though it looks, it's not actually strictly linearly separable. So this highlights the difficulty of learning these models. It's not always the case that the same nonlinear transformation casts them as linearly separable. Now, if we flip the orientation of these units, so the parameters are now changed, the decision boundaries are oriented the same, but the parameter vectors point in a different direction. We can look at what happens in this case. First, in terms of the 10-8 activation units, they are symmetric in terms of the sign flips. As a result, you get a problem now again that's linearly separable in terms of the output unit attached at the end operating on these F1, F2 coordinates. Now, in this case, in terms of the flipped orientations, now you can see that the positively labeled points are always on the negative side of these decision boundaries. As a result, they are all squashed down to zero. All the positively labeled points appear in the origin. Now, in this case, the problem is actually linearly separable, even with the ReLU activation units. So we can take another look. What if we didn't choose the units somehow wisely? We actually chose them at random. So this is a particular specification of the hidden units, their parameters, now visualized as random choices of the decision boundaries and their orientation. If you look at how the points are transformed now, for example, with the 10-8 activation, you don't actually get a separable problem in terms of the hidden unit activation coordinates. However, we can introduce some redundancy here, not only map it from two-dimensional points to two-dimensional hidden unit activations, we can introduce more randomly chosen hidden units. So in this case, I take the two input coordinates x1, x2, map it to 10-dimensional hidden unit activations. So I have 10 hidden units, all of them connected to the input units, but with different parameter settings that are chosen at random and visualized here as randomly chosen decision boundaries and their orientations. Now the question is not whether the problem is separable in two-dimensional space, but whether it is now separable in that new 10-dimensional space. Notice that this is quite similar to the systematic expansion that we did earlier in terms of polynomial features. Now we are choosing those features at random, but it's a different random choice, so a different perspective to looking at the data, and we construct a longer feature vector based on those transformations. So we would expect that in this case, the problem might actually become separable in that new 10-dimensional space. And indeed, that is the case. So let me try to briefly visualize how that happens. So I'm going to plot a two-dimensional version of that 10-dimensional hidden unit activation space, how the original points are mapped to 10-dimensional coordinates. I'm trying to find a two-dimensional version of that highlights points are really separable now in that 10-dimensional space. So I can actually find these coordinates by training a classifier in that 10-dimensional space and taking the classifier direction as one of these coordinates and then taking the second best that's orthogonal to that as the other coordinate. And you can see indeed that in this representation there would be output classifier that would correctly classify these points. So introducing redundancy here is actually helpful. And we'll see how this is helpful also when we are actually learning these hidden unit representations from data. Introducing redundancy will make the optimization problem that we have to solve easier. All right, so what we've seen so far is that we can construct complicated neural networks with layer-wise processing based on simple units that act like linear classifiers. So we have an input layer, we have potentially multiple hidden layer transformations until we get to the output layer, which is the prediction that we actually want. And the role of the hidden layers is really to adjust the transformation, adjust the computation in such a way that the output layer will have an easier task to solve the problem. Problem now becomes actually learning these representations together with the final classifier, and we will talk about that in the next lecture. Welcome back. Today we're going to be talking about feed-forward neural networks, and in particular how to learn them from data. If you recall, feed-forward neural networks with multiple hidden layers mediating the calculation from the input to the output are complicated models that are trying to capture the representation of the examples towards the output unit in such a way as to facilitate the actual prediction task. It is this representation learning part, you're learning the feature representation as well as how to make use of it, that makes the learning problem difficult. It turns out that a simple stochastic gradient descent algorithm actually succeeds in finding typically a good solution to the parameters, provided that we give the model a little bit of overcapacity, and it will become clear later what this means. The main algorithmic question then is how to actually evaluate that gradient, the derivative of the loss with respect to the parameters. And that can be computed efficiently using so-called backpropagation algorithm. So here I have a simple example of a feed-forward neural network. I have input units here, each unit holding one coordinate of the input example. The network evaluates a complicated mapping then using parameters collectively W, parameters mediating each of the layer-wise transformations, getting to output here, and for simplicity that could be just a single output unit. So that output is now actually a complicated function of the input as well as the parameters collectively W. All the parameters in the model will impact how the network responds to that particular input X. In training, we are also given a target Y. And so our task in applying stochastic gradient descent is simply to evaluate for each example now a pair of input and the desired output Y. We want to adjust the parameters in the model so as to nudge them in the reverse direction of the gradient. So what we have to do is to evaluate some loss that measures how much our predicted output differs from the desired target. So we evaluate how that complicated neural network output as a function of input and the parameters differs from the target output, and we take a derivative of that loss with respect to each of the parameters. So for example, with respect to parameter at the nth layer mediating how the ith unit in the preceding layer affects jth unit at the nth layer. And we simply apply a stochastic gradient descent algorithm by nudging those parameters in the reverse direction of the gradient, multiplied by some step size parameter eta. So the main question here is, since the mapping is complicated, how do we actually evaluate these derivatives? And we can do so efficiently by a so-called backpropagation algorithm. So let's take a very simple example of a very deep network that only has one unit per each layer. This is to illustrate how backpropagation works without making the notation cumbersome. So we have as an input only a real scalar value x that's propagated through the network, and as an output we have a simple scalar fl. Now the network computes that input-output mapping simply as follows. Its unit here, z1, is an aggregate input of the signal from before, and it is just the input example times the associated weight, and we will forget the offset parameter for simplicity. So the activation or output of the first unit is simply now, say, 10h of z1, which is x times w1. And similarly all the way to the end, the last unit is now just 10h of the activation of the previous layer unit times the associated weight WL. Typically, the last unit could be linear, but we are going to retain the same form just for simplicity. Now, we are, in addition to x, we are given the target value y, and we have to evaluate some loss between the desired output and the network prediction. Notice that the network prediction here is a function of all the weights in the model as well as the input example x. And that loss could be, for simplicity, just a squared loss if it's a regression problem, or it could be a hinge loss for classification or other loss. Now, in order to understand how we can propagate the training signal from where we observe the output y all the way down to parameters that we are actually interested in modifying, we need to understand the individual mappings between the layers. So we need to understand how the previous layer output is transformed into the next output using the parameters WL. And it turns out that in order to propagate that signal backwards, the only thing that we need to really understand is how the output of this box changes as a function of the input, the derivative of the output with respect to the input. If we can calculate that, then we can actually propagate the signal, the training signal, from the output where we observe it to the parameters that we are interested in modifying. All right, so let's continue with this example. We have an input example x, corresponding target value y. We can evaluate a loss at the output, so how much our prediction differs from the target value. Now, what we need to evaluate in order to adjust the parameters w1 is the derivative of that loss, and I'm just going to write it as a loss rather than always writing loss of y and fl. We need to evaluate the loss, how a loss changes with respect to changing the parameter w1. If we can evaluate that, we can apply a simple stochastic gradient update rule to adjust the parameter value w1. Now this can be written in two parts. We can understand how changing w1 changes the output of that, or activation of that unit. So if we modify w1, how does the activation changes, and then how the activation affects the ultimate loss. So asking the question, if we could change the activation a little bit, how would the loss change eventually? So these are the two things that we need to compute. The first part, we know how to compute, since the activation is simply a 10/8 of x times w1. Its derivative is simply a derivative of 10/8, which is 1 minus 10/8 squared, or 1 minus f1 squared, times then what remains from the argument, x times w1, take the derivative of that with respect to w1, and you get x. So what remains is to compute that derivative. And this is what we're going to propagate through the network. So let's see how we can evaluate this quantity on the basis of the analogous quantity a little bit closer to the end. So we would want to evaluate how the loss changes as a function of the output f1. And now we can ask how f2 changes as a function of changing f1, since f2 is a function of f1, and then how the loss would change as a function of f2. So if we've already evaluated this for the second unit, we can hop backwards by just understanding that mapping of how the individual layer-wise mapping works, how the output changes as a function of input. Okay, since f2 is just computed as a 10/8 of f1 times w2, we get a similar expression here for that mapping. We get just the derivative of 10/8, which is 1 minus f2 squared, and then derivative of the argument with respect to f1, and the argument was just f1 times w2, so what you get here is just w2. Okay, so if we have this quantity for the second unit, we can easily compute it for the first one, so we can move backwards. So now let's look at how we hop backwards here. We can take here derivative of the loss with respect to FL. That we can easily evaluate. So for example, if it's a squared loss, we can evaluate it as a derivative of the squared loss between the target and our predicted output with respect to FL. And it will just give minus y minus FL. So we can easily evaluate it when we have the predicted output and the target value. Okay? By the equation that we just looked at, this one, we can hop backwards by multiplying this derivative by a mapping of how FL changes as a function of the activation of the penultimate layer. And we can move backwards here by multiplying always by Jacobian between the output and the input. Here we get derivative of f3 with respect to f2. We get derivative of the loss with respect to f2. Finally, we evaluate derivative of the loss with respect to f1. And to get that from the quantities we've already computed, we need to multiply this further by this Jacobian. Okay, the whole product is now the loss, derivative of the loss with respect to f1, which is the quantity that we wanted to compute. So backpropagation is simply computing these quantities that we want at a point where we need to adjust the parameters, propagating this training signal from the output where it's available all the way down to the parameters that we are interested in modifying. Now, based on the nature of the calculation, the fact that we evaluate the loss at the very output, then multiply by these Jacobians, also highlights how this can go wrong. Imagine if these Jacobians here, the values, the derivatives of the layer-wise mappings are very small, then the gradient vanishes very quickly as the depth of the architecture increases. If these derivatives are large, then the gradients can also explode. So there are issues that we need to deal with when the architecture is deep. So let's take here a few visual examples just to see how the network evolves as a result of stochastic gradient descent updates. Here I have represented an initial network where I have the two input coordinates x1, x2, and two hidden layer units, and a final classifier f here, and I've illustrated how those hidden units as linear classifiers are initialized. I've also plotted on the left how the average Hind's laws of this classification task evolves as a function of iterations or epochs. So each iteration is running through all the training examples, performing a stochastic gradient descent update in random order of the training samples. So as you can see, after a few runs over the training examples, the network actually succeeds in finding a solution that has zero Hind's laws. So it correctly classifies all the training examples. So let's look at what that eventual solution looks like. Here is an illustration on the left. The hidden units, again as linear classifiers, how they have evolved to provide a representation that makes the classification task easy. And indeed, in those two coordinates, f1, f2 coordinates, if we plot all those training examples in terms of hidden unit activation coordinates, then the task for the final unit is quite simple as a classification task. So we found a good representation entirely by learning that facilitates the classification task for the final unit. We can now look at also what happens when we add more hidden units. So I no longer have just two hidden units operating on x1 and x2. I have 10 of them. So I have f1 through f10. And then I have a final unit here that takes as input that 10-dimensional hidden unit activation and tries to classify it. So we can now see how these 10 hidden units evolve as linear classifiers after training. So what you can see here is that many of those hidden units end up doing something useful for the classification task. They look similar to the two hidden unit solution, but some of the others are actually still doing rather random things. So this is an issue here with giving the network overcapacity, giving it more units than it actually needs to solve the problem. And as we learn and arrive at a perfect solution in terms of end-to-end mapping from inputs to outputs, then in that solution, not all the hidden units need to be doing something useful, so long as many of them do. Here's now an illustration of, just in terms of decision boundaries, what happens when we try to solve a harder task. Here I'm solving it with 10 hidden units. It finds a decision boundary now over the original coordinates, so it's a complicated mapping, and it finds a decision boundary that correctly classifies these examples. I can even increase the number of hidden units here from 10 to 100, but you can see that there's some odd part of the decision boundary here. We would rather not have it there since it is not implied by the task. So where does it come from? So it turns out that when I solved this problem, run the example, I initialized all the hidden units as classifiers by setting the offset parameter to 0. So all these initialization of the hidden units as classifiers, they were concentrated at the origin. Okay? And that effect persists in the solution because there's nothing to change that. It's not necessary to change that. So if I randomly also initialize the offset parameters, I will get a very nice solution without such phantom boundary looming in the empty space. Let's now look at an example where overcapacity helps optimization. To this end, I've used ReLU hidden layer units, so the activation functions for their hidden units are rectified linear functions, so they simply squares their negative values to 0. Now, with 10 hidden units, sufficient to solve this task illustrated here. But if we run the stochastic gradient descent algorithm, it does not find a separable solution. Some of these examples are misclassified. So as an optimization problem, it is still hard, even though the separable solution exists. But if I give it overcapacity, I give 100 hidden units, it finds a very nice separable solution. Recall the case where we introduced more hidden units earlier and actually looked at visually what they end up doing. Now, the same would be true here. Many of those hidden units are not actually perfectly adjusted to this task. It is sufficient that only some fraction or many of them do. The randomization inherent in the initialization creates some smoothness, and we end up with a smooth decision boundary even when we have given the model quite a bit of overcapacity. And you can see this even if we gave 500 hidden units, ran stochastic gradient descent, and we end up with a very nice decision boundary as a result. So in summary, neural networks are complicated input-output mappings. They try to learn the representation of the input that is actually useful for the classification task or regression task. And we can solve that learning problem with simple stochastic gradient descent algorithms. The derivatives that are needed to be computed for stochastic gradient descent updates can be evaluated efficiently via backpropagation, even for deep architectures. Now, since these are complicated models, they cannot find a globally optimal solution, but they can find a locally optimal solution, which is typically quite good. In particular, we can facilitate the optimization of these architectures by giving them overcapacity, making them a little bit more complicated than they need to be to actually solve the task. We will later talk about regularization, how to actually squeeze the capacity of these models a little bit, while in terms of units giving them overcapacity.